Good afternoon. So I'm going to give a brief overview of the work we have done in the deep level chair over the last 4 years. Yes? So we are all familiar with what the XAI is. So we want to help humans understand machine learning models. In Europe, there is an effort to categorize the risks involved with machine learning models. And so this is essentially, there is a pyramid, and after this level, risk can be unacceptable, or we can have high risk. And examples of high risk include, for example, creditworthiness, law enforcement, management, and operation of critical infrastructure, and so on. Okay, so this, of course, is not yet a law, but Europe is trying to approve something that will become law in the European Union. And what we have been doing, besides this, of course, we have safety critical systems, and over the last 4 years, we focused on computing explanations in this setting. So, of course, what I'm going to talk about is not something most of you are familiar with. What you are familiar with is what is shown in this slide. So you are familiar with probably with this paper, or this paper, or this paper, or this paper. And if you are not familiar with the papers, you are familiar with the acronyms. So this LIME is for this paper, SHAP is for this paper, ANCHOR is for this paper, and intrinsic interpretability up here is for this paper. What we have done over the last 4 years is to prove that all these hallmarks of informal or non-formal XAI are wrong. And I'm going to try to convince you of that. Okay, so let me start first by giving you some context of what I'm going to talk about. So everybody's familiar with very simple machine learning models. This is a decision tree. And in this talk, I'm going just to use zeros and ones to make things very easy to understand. But of course, we can map things. So when I show this tree, actually, I could be showing this tree. So what is an explanation? For us, an explanation is answering a why question. So why the prediction? Okay? And we see that as a rule. So if some condition holds, then we guarantee that we have the prediction. It's a very simple definition of explanation. Okay? And so for us, an explanation is just a set of literals or just the features that are in this condition here. And of course, irreducibility matters because we want to give users something that you cannot simplify further. Okay? And so let me go back to this example and suppose that my input is not x1, not x2, and x3. So what would be an explanation? In this case, a possible explanation would be, well, as long as I have not x1, not x2, and x3, you guys agree with me that I'm going to predict x1. So I could say, well, that's my explanation. Okay? You could say, but it doesn't really help here. I'm going to show you cases where we have something that is much simpler than this, of course. So, so for us, when we talk about answering a why question, essentially, we want a set of features that is sufficient for ensuring the prediction. So we represent this with this logic statement. So we look at all points in feature space, and if we fix the guys in X, then we guarantee that the prediction is what we want. It's a very simple logic statement, which we can analyze with logic tools. And of course, what I'm stating here is just a rule. So if these guys are true, then I'm going to guarantee the prediction. It's just a rule, nothing else. Okay? We have also looked at other types of explanations, which are the why not explanations. And again, it's a minimal set of features, but in this case, it's sufficient for changing the prediction. So I want to get something else. Okay? And in this case, I changed the logic statement, but it's actually quite related with the previous one. And what we did is that we proved that actually we can map one to the other and vice versa. And we studied a bunch of other problems related with these two types of explanations. Okay? So what have we done over the last 4 years? Essentially, we started by proving some tractability results. So for a bunch of families of classifiers like decision trees, monotonic classifiers, naive-Bayes classifiers, and so on, we proved that we could compute one explanation in polynomial time. Okay? So that was very good news. Well, why is it very good news? Because the plot shows that, well, it's in practice, it's very effective because we can compute in polynomial time. So we are very, very happy. That's why I show green. Some other problems, well, we showed they were computationally hard. So meaning in the worst case, they will take exponential large time to solve. But what we did is that we developed logic encodings that allowed us, even though the problem is hard, we were able to be very effective at computing explanations. Okay? And so I'm going to show you some results shortly. And then the bad news, for some classifiers, we proved that they were computationally hard to solve, and in practice, they were very difficult to explain with logic methods. Okay? So this was until 2022. This year, we changed things a little bit, and we showed now that actually for neural networks, we are not happy yet, but we are much happier than before, or less unhappy than before, because we now can compute explanations in more serious cases. And I'm going to show you some results. Okay? So this is a plot. Of course, you guys are not going to pass the plot. So this is just a lot of information about explaining with random forests with, well, one method. And here is the running time, the average running time, as you can see here. And the only message I want to convey is that we compared with Anchor, which is one informal explainability method. And as you can see from here, so this is the average running time, so we are usually much, much faster than a heuristic method, and we compute exact explanations. Okay? And we are not looking at trivial problems. So for example, here, the random forest has 44,000 nodes. So this is a huge random forest. And we have a few other examples that are pretty large. So for random forest, we can be very efficient. For neural networks, this is where we started in 2019. So a bunch of data sets, very small, I'm going to talk about that. So this was the first rigorous approach for explaining neural networks. And at the time, we could scale to a few, and few would mean at the time 20 neurons. So we could explain neural networks with around 20 neurons. Okay? Now in 2023, we can do much larger. So some of you guys are familiar with these data sets. And now we can explain neural networks with a few hundred neurons. Now, this is more important than being able to explain neural networks with a few hundred neurons, because if robustness tools can look at bigger neural networks, then we can explain bigger networks as well. So we can map whatever is done in robustness to explainability. Okay, so in terms of tools, if you guys want to play with the tools, we have lots of tools. So for naive Bayes and linear classifiers, GitHub repository, monotonic classifiers, decision trees, tractable circuits, decision lists, random forests, tree ensembles and boosted trees, and probabilistic explanations for decision trees. We have a few more, but they are not yet publicly available. Okay? So of course, besides computing explanations, we discovered that there was a lot more to investigate. And so this is a timeline of the things we have been looking at, we and our other groups. So besides computing explanations, we investigated duality, tractability, queries, input distributions, probabilistic explanations. Now we are looking at feature attribution, and so on and so on and so on. So this is what we have. It's not just computing explanations. What we also do is investigate a bunch of other problems. One, for example, a very recent one is to certify the algorithms that we use to compute explanations, for example. Okay, so I promised you that I was going to disprove all the hallmarks of non-formal XAI, so I'm going to do that for you now. So let me start with the easy one, and then I move to the other ones. So I'm going to start with this one, then I'm going to talk about these two guys, and I'll finish with the Shapley values, okay? So let me start with interpretable models. So my claim is that interpretable models are not interpretable. So let me explain why. So this is a paper from NeurIPS 2019, this optimal decision tree. When I say optimal, it means you cannot get a smaller decision tree, okay? So it's the best you can get. So again, this is not our paper. Someone else was proposing 4 years ago to get these optimal decision trees. And I'm going to pick one point in feature space. So I'm going to ask for an explanation for 0, 0, 1, 0, 1. Okay? Yes? So 0, 0, 1, 0, 1. So we should be here. Yes? So essentially, given what I said at the beginning of my talk, the explanation could be if not x1 and not x2 and x3 and not x4 and x5, then the prediction is 1. So when the guys in this paper say that they do interpretable, they are saying, well, the path is the explanation. Okay, so this is what they are saying. Because they say we don't need explanations, the tree is itself the explanation. So what we concluded and we proved is that actually things can get really bad, because for this path in concrete, if you flip all the values of these features, 1, 2, and 4, you don't change the prediction. Doesn't matter. So the point is that we can find an explanation, one of our objective explanations, and say it's just 3, 5. As long as we fix 3 and 5, the prediction is 1. Everything else is irrelevant. Okay? And so, of course, the guys that say you should use interpretable models will give you this. We can give you this. Any human being that is a human being will agree that is a much simpler explanation. Okay? Let me continue. So you could say, oh, come on, this is just a very trivial example. What happens in real life? So this is an example from real life, a medical application. And this is a path. And the authors were not kind enough to give me the tree. So I decided to look at the tree and do the analysis by myself. So I cannot, but it's like this. The prediction is orange. So any branch that is predicting orange, like these guys, are irrelevant. And so I have a path with 19 internal nodes just by manual inspection, because I cannot do the actual inspection. At least 10 literals are redundant. So I can drop, because there is one that is duplicated, I can drop 9 features. So this, for people that are aware of the cognitive limits that we have, we human beings, going from 19 to 10 is very significant, okay? And this is a real decision tree. But what we proved actually is that redundancy can be arbitrarily large on the path length. So if you have a tree with a length of 100, we can actually find examples where the explanation is size 1. Okay, so it's huge difference. Okay, can I continue? Yes? Okay, so since 2019 we have been shouting, but nobody has been listening, that if you do model agnostic explanations like Lime or anchors, you are going to get errors. And so for boosted trees, we had to do boosted trees because at the time we could not do neural networks. And so I'm going to show results for boosted trees just because of that reason. So what we do is we use formal explanations to prove that the non-formal explanations are incorrect. And this is what we got for anchors back in 2019. So for a bunch of data sets, this is the percentage of explanations that we got that are incorrect. They are not explanations. Okay? So let me put this in plain English. Most often, the rules that anchors produces are not rules. They are wrong. Okay? 99.4% of the time, 99.7% of the time. Okay? There are exceptions, of course, but we are talking about high-risk applications, so you don't want exceptions, or the rule anyway. So we change a bunch of things. So instead of just saying it's incorrect, we counted how often it is incorrect. That doesn't change the picture. We used, because here if you need to count, we have to use a different type of explainer. We did that, and again, it doesn't change the picture. We did the same for feature attribution, and we got similar results. So it doesn't change the picture as well. So this slide disproves 2 of the papers I mentioned before. So it's actually quite crazy, because you can get scenarios like this one, which I showed here, I think, last year. So you can have a classifier for deciding bank loans, and you have 2 samples, Bessie and Clive. This guy is, for Bessie, she gets the loan. Clive is unlucky, he doesn't get the loan. And it could easily happen that the explanation is X, 45 and 50K, let's say. And it could happen that X is consistent with Bessie and consistent also with Clive. So the reason for Bessie to get the loan is X, and the reason for Clive to get the loan is also X. Okay? So it means nothing. It's completely incorrect. Okay? So let me give you the dessert of the talk. So I was just checking actually, and CHAP, the paper on CHAP is the last one. It's from 2017. It now has 17,000 citations. So just this year it got more than 6,000 citations. That's a lifetime of research for many people. Okay, so it's pretty significant. So let me prove you that actually it's more important. So what I'm going to prove with this slide is that it's not that CHAP is wrong. The theory behind CHAP is wrong. Okay, so I repeat, the theory behind CHAP is wrong. So let me prove why. Well, I'm not going to do the full proof, but I'm going to give you the details. So I have an example decision tree here, and an example decision tree here, and you guys agree with me, they are very, 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 very similar. Yes? Yes. So here I have the classification functions. So essentially, I'm just swapping 3, 0, 0, 3. Yes? Seems harmless, right? So let me continue. So I'm going to look at this instance, 1, 1, 1, and then the prediction is 1. It's going to be here, and it's going to be here, okay? And I'm going to say what features are important. Again, you guys can help me here. Which features are important for me to say decision 3 predicts 1 and decision 2 predicts 1? Which features are important? One is okay. 2 is not bad as well. So if I fix 2, I'm still safe. So even if I change 1 with 2, I'm still safe. So as long as I fix 1 or I fix 2, I'm fine. Yes? Now let me ask you a different question. Suppose I decide to change 3. Does it matter? I can do whatever I want with 3. I will not change the prediction. Yes? Yes. Okay. Very good. So this is the exercise we did. So we computed explanations, and this makes sense. So because, as I said, if I fix 1 or I fix 2, I fix the prediction. And if I want to change the prediction, I need to change 1 and 2. Okay, I'm not explaining how you compute this, but if you are interested, then I can explain. Okay, for the second decision tree, it's the same. Again, they look the same, so it makes sense again. Yes, yes. So if you guys, some of you guys are crazy about adversarial examples, you look at adversarial examples and you get the same. So adversarial examples on Hamming distance, minimal Hamming distance, right? So here the smallest Hamming distance to change the prediction is 1, 2. You need to change both. And here it's 1, 2. You need to change both. And you really don't care about 3 because no matter the value of 3, the prediction has changed. Yes? So let's compute Shapley values. So this is what we got. Okay, so it's not clear. Okay. Let me change the color. Oh, it doesn't change the color. So what happens is that for this tree here, the Shapley value of the important features is 0, which according to the religion of Shap means no importance. And the feature 3, which is the most completely relevant feature, as you guys can conclude, has weight. So it matters more than 1 and 2. Okay? So the punchline, okay, so the punchline is that they are not okay, but the punchline is that you can get incorrect, completely incorrect results in theory, not to mention in practice. Now in practice, it's even worse. What we observed is that if you run the tool Shap, most often you don't agree with the Shap scores. It's even worse. You don't even agree with the ranking provided by Shap scores. So Shap scores are the theory for Shap, but they don't respect the Shap scores. Okay? And of course, the theory where they start from is already misleading. So you have 2 errors, 1 error on top of another error. So if you get anything mildly correct, it's a miracle. Let me continue. So this is what I did. The take-home message is wrong, 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 wrong. And we proved it, okay? So if you are going to use explanations for high-risk or safety-critical applications, please don't use non-formal XAI because you are going to get wrong results, okay? Very good. And of course, this means it's completely unsuitable for trustworthy AI. So this is what we have been saying for 4 years, but we have not shouted loud enough. Actually, by the way, the only thing we proved recently is that Shap is incorrect as well. So everything else we have known for several years. Okay, so what are we doing? Well, we are doing a few more things. Right, so because we are humans and we don't understand complex explanations, we are trying to find distance-restricted explanations because they can be smaller. And this makes a nice link with adversarial robustness. Number 1, we are doing certification of formal explainability, meaning not only that the algorithms are correct, their implementation is also correct, okay, so that we don't make mistakes when we compute explanations in practice. We have been looking at more expressive explanations. So instead of using equality, for example, if my height is 176, that is really not very, does not give a lot of information. If I say that as long as my height is between 170 and 180, this is much more informative for someone that is trying to understand why the prediction is made. Okay, so we are still trying to understand the limitations of Shap scores, the exact ones, not even the tool. We are inferring input constraints. Why? Because in many settings, not all points in feature space are possible. So more tractability results. We have a paper this year on oblique decision trees, for example, that we can, in some cases, we can do. It is tractable. And as I said before, reduce explanation size because we have serious limits on what we can understand. So we'd like to compute explanations that are as small as possible. That's it. Thank you very much.
Yes, question from Claire.
No, give me a second. So I have to go back a few slides. Yes, another more, a little bit more. Yes, we are. Oh, not yet. Here. So your question is. So here is the number. So the size of the XP is shown here. Okay. So what we did over the last year is that instead of using explanations that relate to the Hamming distance, we relate with any type of distance, and we can compute what we call distance-restricted explanations. Okay. And so these are explanations that are hold. So as long as you fix the features within that wall, you are going to get a prediction. Okay. No. If you give me the instance, I will. So here I have the information. So I have the number of calls to the oracle, the adversarial robustness oracle, and here I have the size of the XP. So these are the features that I need to fix. I cannot change. The other ones I can change. I can put any value. Okay. So for example, I think I understand your question. So for example, here 0 means no matter what I do with the features, I will not change within the ball that I fixed. Okay.
Sorry, I'm not an expert at all, but I was wondering. So I think I understand your point about getting really the explanation or the minimal explanation for something. And if you think about what people do with a machine learning method, you have quite often a black box in the middle, and you may be interested in an explanation that would be true for a significant trials, a number of trials. For instance, my explanation is not always true. I have counterexamples, but maybe with a 90.5% of chances, it will be correct. Of course, for very, as you say, when there are humans, it's not maybe something that you would advocate, but just as just to think about something in a mathematical sense. What would you? Yeah.
Yeah, the answer is bullet 8. So what we are doing is not only exact explanations, but also probabilistic explanations. So they are not always true, but they are true with a high probability. So 98%.
And okay. The other tools for which you showed that they were wrong on some instances.
Yeah.
Do you know what would be probabilistic score?
Yeah. So this is what I mentioned in passing here. So the results were not positive, even if you count. So counting means you measure the probability. Even if you count, the results are not positive. So the guarantees that you get are like 60%, which really, or 50%, which 50% is it's really bad. Yes.
Thank you. Let's thank Joao for the talk.